my name is Sandeep. I'm a developer advocate at Google Cloud. I like buzzwords, so I threw them all on a single slide. I like alliteration too, so I try to pick ones with all M. Microservices, machines, mobile, and more with containers and gRPC. So before I get started, how many of you know what Docker is? See, if I asked that question like 2 years ago, everyone would be like, huh? What are you talking about? So I like that a lot. I don't have to go through what Docker is anymore. How about Kubernetes? Very cool, cool. And gRPC. Okay, very cool. That's exactly what I expected. The hands keep going up more every single time I ask that question, which is really cool. So you can follow me on Twitter if you want to, at Sandeep Dinesh. But what I want to talk about is our Lord and Savior, microservices. Who has heard that microservices are going to save us from everything, from all our development hell, right? It's going to save us. And you know, everyone thinks that because everyone's searching for it on Google. If you've ever been to another microservices talk, which talks more about the philosophy of microservices and what it does to your organization, you know that what you're doing is you're taking a lot of complexity in your code and you're moving it to your organizational structure. Now, sometimes it's easier to scale one than the other. It's a decision you have to make. Microservices, what is it? You write a program that does one thing and that does it really well, and then you compose them together, right? So instead of having a very big monolith that does everything, which makes it hard to tweak and deploy, instead you have multiple smaller applications that communicate and are deployed independently, yada, yada, yada. It's the typical Unix philosophy. So why microservices? Again, there's a ton of reasons. Continuous deployment, robustness, polyglot development, maintainability, scalability, blah, blah, blah. But what I really want to talk about more is how microservices, and specifically how one way at Google that we kind of prescribe to the peoples that are you and me. So how many of you have heard of Borg? Wow, that's surprising. How about Stubby? That is not surprising. So Borg is Google's internal container scheduler, right? So around 10 years ago, we decided to use containers inside Google, and no one was using containers outside Google, so we had to write our own stuff. So Borg is how we actually schedule pretty much every single application at Google, from your little side project that you want to run in a cluster to like Google search. And so you have all these containers running around in production. They have to talk to each other, right? They have to have some sort of RPC framework to actually communicate with other services, right? The Gmail user service has to talk to the auth service, which talks to the data service. I'm just making things up. Those are not real services. What it uses is a system called Stubby. So Stubby is our RPC framework. Now, what we could have done is taken Borg and Stubby and put it on GitHub and been like, haha, we have open sourced, we are good community members. And then people have just look at it and be like, this is the worst code I've ever seen. Because it's literally tied so deeply into our infrastructure that no one could understand it. I don't think anyone at Google can understand the whole thing. So instead, what the idea was, let's do a from scratch reimplementation of these things, starting in the open source community, right? So Kubernetes, 100% rewrite of Borg. It's like third generation container scheduler written in Go, and gRPC is very close to Stubby, but it's using HTTP 2 and protocol buffer 3. But that's all just buzzwords. Let's take a look at what these two actually give you when you're running microservices. So Kubernetes. So a lot of people here know what Kubernetes is. For those of you who don't know what Kubernetes is, right? So you have your Docker container, it has your code, it's running, it's great on your local machine. Now you want to deploy it to your production cluster or whatever, and now it becomes more complicated, right? You're doing the same thing as before. You're SSHing into a machine, Docker run, and then keeping it up with some like NoHub or something like that. Terrible, terrible things. You haven't really done anything except made your development a little bit easier. With Kubernetes, it manages and orchestrates those containers on your cluster for you, right? So you're no longer dealing with machines, instead you're dealing with the cluster and the Kubernetes API, which is way, way easier to manage. So it looks something like this. You have your app, you put it in a Docker container, it's great, right? It's Dockerized. Now it can run anywhere. All right, but let's actually run it. In Kubernetes is an idea of a replication controller, in this case a deployment. And a replication controller is actually a really cool concept. Basically, you tell Kubernetes, I want this container, and I want 4 copies of it. That's all you tell it. And it just says, OK. And it starts running it on your machines for you. You don't have to tell it which machine to run on. You don't have to tell it if it crashes, please bring it back up. It's all automatic. So it can be like, all right, I want 4. OK, you have 4. One crashes, it'll spin it back up on another host. A host crashes, it'll redistribute all those containers to another host. And you don't have to worry about any of that stuff. You just tell it what you want, and it'll do it. But of course, if you have these random pods and containers spinning up on random computers in your cluster, you have to have some sort of layer on top that can route traffic to the correct Docker container, right? And that's where a service comes into play. So a service is a static IP address and a DNS host name that'll route to a dynamic number of these containers running on your system. So 1 or 1,000, it doesn't matter. You just hit that one service and it'll load balance traffic to the containers in your cluster. Basically, you take all of that and it becomes a microservice, right? So you have your code running in the containers and your service endpoint that's a static IP address, and everything, it gets bundled up, and that's your microservice. So this is an independently deployable piece. That's pretty much it. That's Kubernetes 101 in like 1 minute. And the thing is, because it's just one cluster, you can actually run multiple microservices on the same cluster, right? That's the whole point, increased resource utilization. So you can say, I want to run these 4 microservices. I don't care where the actual code is running. I just tell it, like, I need this much memory, I need this much CPU, I don't want it to be running with this container or whatever, and Kubernetes will take care of scheduling it for you, right? So you have 4, you can scale one up independently of the others, scale one down independently of the others, roll one up without any downtime, and then basically you create the Microsoft Office logo, which is the goal of software engineering. All right, so in the few minutes I have remaining, let's actually build some stuff. This is my machine learning application called Hello World. Everything we do at Google is machine learning. And basically what I want to do is deploy it, right? So my first step is Docker build. As you all know, is how you build a Docker container. I'm going to give it a tag called gcr.io project frontend 1.0. And so GCR is our container registry. It's a secure place where you can store Docker containers. Quay.io, Docker Hub, just similar things. And then gcloud docker push will securely push that container up to the cloud. So the first thing is the front-end service. So what this is going to do is it's actually going to create that static IP address, and it's going to forward traffic from port 80 to port 3000, which is where our app is listening. And it's going to select every single container with the name front-end. And then this type load balancer is actually going to spin up a Google Cloud load balancer. So if you're running on AWS, it'll spin up ELB. On Google Cloud, it'll spin up a network load balancer, things like that. So let's actually deploy this. So I can go cube, CTL, deploy, apply. Front-end service, YAML. So all I'm going to do is read in that file and then hit the Kubernetes API. So I already have a cluster created. In the background, I had it in the oven ready to go. So now I have the service created. So if I can go cube, CTL, get service. And you can see that I have a front-end service up and running. The cluster IP is that internal IP address, and the external IP is still pending. So it's spinning up that load balancer. OK, so now we have that static IP. Now we have to actually run our code. So here is how you do that. Again, it's a simple YAML file. We have 2 replicas that we want to run. We can change that later. The name is front-end, so that is the tag for our container. We can give it any arbitrary key value pair. The image is that same image I pushed up with that gcloud docker push, and I'm opening up port 3000. OK, so let's do that. Sweet. So now if I go cube, CTL, get pods. So pods is a collection of containers. I only have 1 in this case. So you have 2 of them running in our cluster. Sweet. Now if I go back to the service, still pending. We will give that a second. Oh, of course. The moment I do complicated stuff, it comes up. So if I go to this external IP, we can check it out. So I have the front end, it's the wrong code. Anyway, it's, it's up and running at this IP address. The code was not what I showed you. That's what happens when I don't test this out. So we have the controller and the service running. So the next step is really this communication part, right? So when you have multiple microservices running in your cluster, communication actually becomes the most important part, right? You can schedule as many containers as you want. If they can't actually communicate with each other, it's kind of pointless to have microservices, right? You have to have each one communicates very quickly because your end user is just hitting this one endpoint and it has to go through this giant stack of network calls to get anything back out. Right? Looks something like this if it's simple. Microservice A, talking to C, talking to B, talking to A, talking to D, whatever. You don't know. And then only one of them has a public endpoint, right? So they all have to talk to each other and get that data out. Good quote, biggest issue in changing a monolith into a microservice lies in changing the communication pattern. This goes way deeper than code. I mean, it's changing the communication pattern between your teams and all that stuff too. But just trying to like take your monolith and just breaking it randomly, arbitrarily at any point is not going to work. You have to know what points you have to break it up and which parts can go over the network, right? You're going to add a lot of latency no matter what you use. But what you use is actually really important. So at Google, we have like something like 10 to the 10th, which is a really, really big number, RPCs per second. We really like RPCs. So we invented this thing called gRPC, which stands for gRPC, Remote Procedural Calls. Yes, not Google. I don't know where you got that idea from. Basically, it's a collection of different things that all make building RPCs way better, right? So the first part is protocol buffers. How many of you have heard of protocol buffers before? So gRPC is using protocol buffers v3, which is way better than the previous versions because those were not as good. It takes this IDL, which is basically a way of defining your data model, right? Your API spec. And it's also a wire format. So when you write your data into a protobuf, it's all binary and compressed, which is nice, which is important when you're making a lot of calls. The next thing, which is my favorite part, is it uses HTTP2. How many know what HTTP2 is versus HTTP1? Okay. So the TLDR is speed, right? HTTP2 is way faster than HTTP1. I actually have another talk where I go really deep into like JSON RPC versus gRPC, and I was really surprised at just how much better gRPC was in most of the use cases. So yeah, HTTP2 makes it really, really fast. Things like multiplexing, so it opens a single TCP connection and then sends all the packets over that. HTTP1, which is most people are using for their calls, opens a new TCP connection every single time, which is a lot of overhead. Bidirectional streaming is my favorite part because you don't have to do polling or sockets or server-send events. You can just do bidirectional asynchronous streaming on the same TCP socket super easily, like surprisingly easy with gRPC. And flow control, right? When you have congestion in your network, things slow down. You need to be able to slow this upstream services down as well. And of course, multiple languages, very, very important. Here's a few of them, right? So Python, Node, Java, PHP, Go, blah, blah, blah. When you're running microservices, you don't want to be restricted on what kind of language you can use. So the more languages your platform can support, the better. Obviously, if you have something like Lua that we don't support, you have to fall back to REST. But for the 11 or so languages that we support, gRPC works great. And for Node.js, it's literally npm install gRPC, which is really nice. And mobile first. So this is Simon Says. How many people know what this game is? Okay, good. I like this game. It's fun. I had a coworker named Mark who also liked this game. And so what we did is we made it internet connected because that's what we do. How many people have played with Johnny 5? It's like a Node.js library for IoT stuff. Okay. Johnny 5 is amazing. If you ever wanted to start with IoT, really recommend Johnny 5. It makes it super easy if you're a Node.js developer. So what I did is I wrote some Arduino code using Johnny 5, and I connected that physical box to the internet. It was great. Mark, my coworker, wrote a Go server and a Java client on the Android phone, right? So we had 3 different languages that we're using to build this demo. And so here's our proto file. It's pretty straightforward. It's a request. It sends a bunch of stuff, it sends a bunch of colors, things like that. I'm running out of time, so I'm not going to go through this too deeply. Basically, it looks like this, right? So Node.js guy plugs it in, starts it up, says request to join, I'm 12345. The phone says, hey, I'm 167890, very random IDs. The server says, okay, I have 2 people joining a game. Both of you guys begin. It's your turn to start Node, and it's your turn to stop Java, right? So the Node person says yellow, he presses the yellow button, and then the server says light up yellow on both. And then your turn is over. It's now the phone's turn. Whoever's playing on the phone is really bad at this game. They put red. So it's going to say light up red, and you lose and you win, right? So it's a really simple game, but it takes a lot of, it has to be real time, right? When I press yellow on my thing, it has to light up yellow on his device very quickly. So gRPC seemed like a really good fit for this. So what I'm going to do is a quick demo of this right here. I don't have the physical device because I literally forgot it at home. I'm not going to make any excuses. So what I'm going to do is actually run a Node.js server on this machine, which is going to proxy it to a web interface. So here, let me turn up my brightness. I'm going to connect to the server on my phone, and it's going to say your turn, and I'm going to refresh this page right here. All right, so I'm going to click blue, so it's the other player's turn, and I'm going to click blue, yellow. And so you can see it coming up here, so I can just cheat and read the screen. But, blue, yellow, I'm really good at this game. And then let's pick red. Oh, other player's turn, okay. Blue, yellow, red. Blue, yellow, red, and then green, right? So it's almost instantaneous, and this is over conference Wi-Fi, which is always fun. I'm just going to lose real fast, red. Oh, you lost, and you won, see? Aha. I'm so good, I always win and lose. But that's pretty much gRPC in a nutshell. And the cool thing is that server, that Go server, is actually running in Kubernetes with the Redis database running in Kubernetes, and it's all just being scaled automatically. I have 3 minutes left, so I'm going to see what I can do. So let's just upgrade our app to use gRPC. This is not going to work because I have the wrong front end deployed. That's okay. So this is our RPC that I'm going to upgrade our app to. And its package is geo. There's one RPC call. It takes a point and it returns a distance. Points are just a 2 points origin destination, or 2 floats, right? And a distance is just a float. So you have all these different data types that you can define, and this gets compiled down to a very, very efficient binary format by protobuf. So you have, this is a synchronous RPC call, right? So it takes a request and returns a response. You can do single-side streaming, so the server can stream to the client can stream to the server, or both can stream to each other, like we were doing in the Simon Says demo. So what we do in our backend code is we require the gRPC npm module. We load that protobuf file, which defines our API service, and then we just build that geo service that we saw in the previous slide. So our server, geo service, what we're going to do here is just define the different RPC calls. So distance between is a function call callback, and it's going to call the get distance function, which is it's going to use the Haversine formula to find the distance on the globe between 2 latitudes and longitudes. And yeah, like I said, Haversine formula, interesting stuff. And then we just listen on port 551, which is the default gRPC port. You can listen on whatever port you want, and then server.listen. That's basically it. Now we have our gRPC server up and running. A few lines of code. Again, we build that, push it, and now we have to update our server, our front-end code, right? That's going to call our back-end service. So again, require gRPC, load in that protobuf. And here's the cool part. Because we're using Kubernetes, I don't even have to hard-code an IP address or anything like that. I can just say new geo service backend : 551, and backend will use the Kubernetes DNS to automatically resolve the correct backend without having to do any sort of like environment config or anything like that. It's just all using DNS, which is nice. We send in a request like this, and we just JSON stringify the output getting from our backend service. That's basically it. Build it, push it. Here we go. Backend deployment looks exactly the same as our front-end deployment. The only difference is we're opening up port 551 and we're using the backend container, and I want 4 replicas because why not? I can launch it like that. Backend service, you might notice here I don't use type load balancer, so it is an internal service. And I'm just going to port forward 551 to 551, right? No sort of remapping needed. Launch that service. And I'm just going to show you this real fast because I'm literally out of time. I'm going to say kubectl get pods. So again, we have our 2 front-end pods running. The cool thing is I can do kubectl edit deployment front end. And it'll actually pull up the running deployment YAML. Now, I don't really recommend this because it's weird. I like checking my YAMLs into source control and doing it that way, but I can, if I wanted to, just go here and update this to 2.0. I have no idea what this will do, which is the best. let's see. I don't even know if I have this container pushed. It's edited. All right, get pods. So you can see it turned off those old containers and then spun up the 2 new ones, right? And they're already up and running, which is really cool. So 12 seconds ago that they started up. And so that's like a 0 downtime deployment. And if I want to roll back, I can actually go kubectl history deployment front. And I really hope this is correct. Deployment history. I can't spell. S-T-O-O-R-Y. Spelling is hard. That's what computers are for. All right, I am out of time. I'm panicking now. Get history front end? No, this is all wrong. I forget. But if I remembered, what you can do is actually get the history of that deployment. So it'll show you that first version we launched and the second version we launched, and you can actually roll back to any previous version, right? So deploying forward is important, but I think rolling back is equally important because everyone makes mistakes. Except me, right? So yeah, it's very, very easy to roll back. Again, it's pretty much instantaneous because it caches all the containers on the hosts, which is nice. That's all I really have time for. I don't want to take the next speaker's time, so let me just, if you want more information, links, Google Container Engine, it's a hosted Kubernetes, it's great, one click. Come to our booth, we're doing code labs, if you want to try this out yourself, we are more than happy to help you, and you can win cool prizes. And links, I'll leave that up there. Thank you all so much.